So we've seen the different ways that we can solve for simultaneous equations. And now what we'd like to do is go through and give you some examples using some electronic circuits examples and go through each of the different methods that we've looked at and show you how you would solve a circuit that had one source in it and using different methods. So in this example, we've got a simple series parallel circuit, 3 resistors, 2 in parallel, and we're asked to find the currents and the voltage drops in the circuit. So R1 is a 1K ohm resistor, R2 a 2K ohm resistor, R3 a 3K ohm resistor, and we have an applied source of 20 volts. So in solving the relationships, coming up with the mathematical relationships, let's take a look at how the circuit can be easily solved by using Ohm's law and Kirchhoff's laws, and this is just what we've seen in the past. So the total resistance for the circuit is R1, the series part, and R2 and R3 in parallel. And so as we go through, and you can go through and do this, we're not going to go through all of the math for reducing a parallel down, but we end up with a 1K ohm in series now with a 1.2 K ohm equivalent resistance, which gives us 2.2 K ohms. The next thing we can do then is solve for the total current in the circuit now that we have the total resistance. So we'll know what the current is from the source. We have a 20 volts source and a 2.2 K ohm resistance. So Ohm's law says that if we divide the resistance into the voltage, we get 9.09 milliamps of current. Now we can start looking at some of the voltage drops. The first voltage drop across R1 then becomes 9.09 milliamps times that 1K ohm resistor, or 9.9 volts. Okay, so this helps us because whatever is dropped across R2 is equally dropped across R3. So if we take 9.9 volts and calculate the total voltage drop across that parallel network, we can solve for the voltage drops. So voltage drop 2 is equal to voltage drop 3, and we will call that the current times the equivalent Rx. 9.09 milliamps times 1.2 K ohms gives us 10.9 volts. Okay, so we could have done it either way. We could have subtracted 9.09 from 20 volts and come up with the same value. Okay, so the current then through the resistor R2 then is that applied voltage, or that drop of 10.09 divided by a 2K ohm resistor, and we have 5.45 milliamps. Do the same thing for the current I3 through resistor R3, and we have 3.64 milliamps. So we are able to show here that the current through R1 is equal to the total current in the circuit of 9.9 milliamps. Okay, so that's our first part of that circuit. Now let's work the same problem using simultaneous linear equations. Let's first establish the polarities of the voltage drops across each resistor in the circuit, and then using Kirchhoff's voltage law, let's start at point A, which you can see just above the source, and move counterclockwise around the loop containing the value for E, R1, and R2. So using Kirchhoff's voltage law, KVL, the source minus the voltage drop 2 minus the voltage drop 1 is equal to 0, or the voltage is equal to the sum of the two voltage drops, V1 plus V2. Starting at point A and moving counterclockwise around the loop, then containing the source, R1 and R3, we get E minus the drop voltage 3 the drop voltage 1 equals 0, or we can rewrite that as the source is equal to the drop V1 plus V2. If we express these equations then in terms of the IR drops, the current times the resistance, then we have an expression that looks like E is equal to I1R1 plus I2R3, where we're just using the equivalence of the voltage drops V1 and V2. Substituting our values then, 20 volts is our source, is equal to 1K times the current I1 plus 2K times the current I2. So the equation then for the voltage source, or the voltage drop 1 and voltage drop 2, then becomes E is equal to I1R1 plus I3R3. Substituting the known values then, again, just like we did in the previous step, 20 volts equals 1K I1 plus 2K I3. Recall those are our ohmic values. Now we have two equations that we can solve simultaneously. So in our previous examples where we just did the math, x and y were our variables. In this case, I1 and I2 and I3 become our variables that we are trying to solve for simultaneously. So the first expression has I1 and I2. The second expression has I1 and I3. So we now have three unknowns. We can simplify the solution by reducing the number of unknowns to 2. Since I1 is equal to the sum of I2 and I3, we can rewrite the expression for the current as I3 is equal to the difference in I1, which is really the total current, minus I2. Let's substitute that I1 minus I2 into the other equation for I3. So in rewriting the expression, 20 volts is equal to 1K times I1 plus 3K I3. We can substitute that value for I3, which is I1 minus I2, in for I3, which we've done right here. Okay, so multiply the 3K times I1, 3K times I2. Now we have I1 and I1 terms that we can gather, and we have I3. So we've gotten rid of the current unknown I3 in the expression. So we're left with 4K I1 minus 3K I2. So now let's look at the equations and where we have two equations and two unknowns and solve for the problem. So 20 volts then is equal to the 1K I1 plus 2K I2. 20 volts then is equal to 4K I1 minus 3K I2, which is the value that we just solved for in the previous step. Okay, so we've got that solved then to that point. Solution by addition and subtraction. To eliminate one unknown, we will multiply through by 4. So now we're going to take our expressions here and we're going to multiply through by 4 so that we have 80 volts is equal to 4K I1 plus 8K I2. And now we have terms that are alike in the two expressions. So 20 volts, 4K I1, 2K I2, which is the, actually, went too far here. 4K and 3K, which is this value, this expression, and then the one that we just massaged by multiplying through by 4. We end up with minus 60 volts, 0 for those terms. Those were the terms we were hoping to cancel out by multiplying by the 4, and then minus 11K. So at this point, we have only one current of interest here, I2. So we can rewrite this as I2 is equal to minus 60 volts divided by 11K, which gives us 5.45 milliamps of current. We can then take that value and plug it back into the equation 1421 and solve for I1. So we're going to take I2, 5.54, we're going to substitute it into this expression, which you see here, 3k times 5.54, and now we have the equation only in terms of I1. So we have 20 volts is equal to 4k I1 minus 16.4 volts. Moving our terms around, dividing through by 4k, we have our total current for I1 as our 9.9 milliamps of current. Since by Kirchhoff's current law, I1 is equal to the sum of I2 plus I3, we end up able to solve for I3 by moving the two terms around. I3 is equal to I1 minus I2, which is 9.9 milliamps minus 5.545, and we end up with 3.64 milliamps. Knowing I1, I2, and I3 now, we can solve for each of those voltage drops using the variation of Ohm's law. Voltage is equal to current times resistance, and in each case we put and substitute our values, 9.09 milliamps times 1K, 5.45 milliamps times 2K, and 3.64 milliamps times 3K ohms, and we end up with our voltage drops, just as we saw in the first step, 9.09 and 10.9. Verifying, adding them back together, we end up with our source value of 20 volts. Okay, so the next time around, the next video, we will look at the solution by substitution.